Welcome back, Physical Science, Physics 30. This is part 2 of the FI 1.1 video, looking at gravitational fields and gravitational force. So in the previous video, we looked at the relationship. How does force of attraction change as the distance between objects changes? So we saw that the relationship is what is directly related to 1 over r squared. Newton realized that the force of gravity on an object not only depends upon distance, but also depends upon how massive the objects are that we're talking about. So we're talking about huge objects here. We're talking about Earth and Moon. In fact, it is directly proportional. So what that means is the larger the mass, the larger the force of attraction. So larger masses exert larger gravity. According to Newton's third law, when the Earth exerts a force on the Moon must exert an equal and opposite force backwards because of that Newton's third law. So the force that Earth exerts on the Moon is equal and opposite to the force that the Moon exerts on the Earth. Because of the symmetry, Newton reasoned the magnitude of the force of gravity must be proportional to both masses. So mass of the Earth and the mass of the object. If I'm talking about the Moon, it's the mass of the Moon. So we can come up with an entire proportion here. So as masses increases, if I double the mass, triple the mass, the force of attraction would become 6 times greater. Just simply a multiplying effect there. So ME and MOG are the masses of the Earth and of their object, and R is the distance between the Earth centers. So ideally that radius is from the center of the Earth, because if we're talking about objects near the Earth, we have to consider the Earth's radius as the distance. So it's from the center of the objects. Newton went a step further in his analysis of gravity. In his examination of the orbits of the planets, he concluded that the force required to hold the different planets in their orbits around the Sun seemed to diminish as the inverse square of their distance from the Sun. So even planets going around the Sun decreased by that 1 over d squared amount. This led him to believe that it is also the gravitational force that acts between the Sun and each of the planets to keep them in their orbits. So not only do we have Earth, Moon, we have everything around the Sun experience a force of attraction, keeping us in orbit in our solar system. And if gravity acts between these objects, why not between other objects? Thus he proposed that, hey, wherever you are in the universe, we have this relationship. So every particle in the universe attracts every other particle with a force that is proportional to the product of their masses. So proportional to the, because remember, the alpha symbol is directly related to, so directly related to the products of their masses and inversely proportional to the square of the distances between them. This force acts along a line joining the two particles. So if we change the proportionality to an equality, we have to introduce a constant. That constant is referred to as the gravitational constant, big G. So there we have our universal gravitational force equation. Figure out the force of attraction between any two masses, as long as we know the distance between them. And we have the constant G, which is in fact determined, as we'll see. So on the next page here, M1 and M2 are the masses of the two particles, R is the distance, and G is referred to as the universal constant, which must be determined experimentally. So the value of G must be very small, since we are not aware of any force of attraction between ordinary sized objects, such as if you have a baseball next to another baseball on the table, guess what? There's a force of attraction there, but we don't see it. So G must be really, really small. We see it coming into play when we're dealing with really big objects, such as Earth and something else. The force between two ordinary objects was first measured by Henry Cavendish in 1798. And after this video, you'll see that I have a quick video kind of outlining the experiment that he'd done. I'll also talk about it here. 100 years later, after Newton published the law. So Newton published the law, then 100 years later, Henry Cavendish came up with the value of G. To detect and measure the incredibly small force between ordinary objects, he used an apparatus like that shown in the figure below. Cavendish confirmed Newton's hypothesis that two objects attract each other And the above equation accurately describes the force of attraction. In addition, because Cavendish could measure the Fg, the M1, the M2, and the R, he was able to basically rearrange that equation and solve for G's. So if you know what this is, this, and this, we can isolate G and actually figure that out, and that'll give us the G that we can use for any type of equation. So the apparatus was similar to this. We have a thin fiber and a mirror hanging from the ceiling of a building, a rod here with a mast and a mast suspended on the end. I believe they're very large masses, bigger than bowling balls. And over here, if we bring another mast close to here, since this is on a thin fiber, it's really easy to rotate. So we could get mass 1, mass 2. We could figure out the radius of separation. And we can get an idea in terms of, if I shine a light here, by that deflection, I could determine what force is involved with that. So you get force, M1, M2, R. So it's just a matter of, again, rearranging that equation for big G, and we can get that. And the value of G is found to be this, and yes, it's a really small number, 6.67 times 10 to the minus 11. And of course, it has a weird unit because we're taking force multiplied by the product of the masses divided by r squared, multiplied by r squared divided by the product of the two masses. So that has kind of a funky unit there. The above equation is called the inverse square law because the force is inversely proportional to r squared. This gives the magnitude of the gravitational force that one particle exerts on a second particle when it is a distance of r away. When extended bodies are when extended bodies are small compared to the distance between the Earth and the Sun, little inaccuracy results from considering them as point particles. So if we're talking about a box on top of the Earth, the two objects are Earth and box. Usually we don't worry about taking the radius of the box because the Earth's radius is so large compared to that. Newton was able to show that the gravitational force exerted on a particle outside a uniform sphere is the same as if the entire mass of the sphere was concentrated at its center. So when we're talking about smaller objects, we can get away with doing that. So let's look at this last example here. Can you attract another person gravitationally? So a 50 kg person and a 70 kg person are sitting on a bench close to each other. Estimate the force of gravity, the gravitational force, if they are approximately half a meter apart. So it's like we're having two people sitting on a bench. The radius of separation from their centers is 0.5 meters, and we know the mass of each. So guess what? We could actually figure out, finally, the force of attraction. So big G, 6.67 times 10 to the minus 11. Mass 1 is 50. Mass 2 is 70. Radius of separation, 0.5 squared. So if we figure that out, plug that into your calculator, 9.338 times 10 to the minus 7 newtons. So you can see, it's a really, really small force. Like that decimal is 7 places to the left. But guess what? It is still there regardless. So, and of course, the force of the Earth exerted on us is much larger than this, so we feel that, but there is a force of attraction. If you're out in space, you would experience that even more due to no planet pulling on you. You would only experience that. All right, welcome back, Physics 30. This is, we'll do the last page here. So look at another example here. So now we'll look at Earth versus some other object. So we'll look at a spacecraft. 2 Earth radii. So if this is the radius of the Earth, an equal radius, an equal distance from here to here. So basically it's 2 radiuses of the Earth, or radii of the Earth. What is the force of gravity acting on a 2,000 kg spacecraft when it orbits 2 Earth radii from the Earth's center? So 1 Earth radii is this, 6,380, like we talked before. And yes, I'll have a video showing how that was determined. So 6,380,000 meter sticks. And the mass of the Earth, then man, you're wondering, how in the world can you figure out the mass of the Earth? Well, guess what? If you have this, if you can figure out the force between the Earth and two other objects, we know the radius of the. Once you know the radius of the Earth, then you can figure out the mass of the Earth, and we'll look at that in another video. So if I plug that all in, Fg equals G M M1 M2, where one of these is the Earth, one of these is the satellite or whatever it is. So big G 6.67 times 10 to the minus 11, mass of Earth, mass of spaceship, and the radius of separation. Now, we have to figure this out, right? Because we have the radius of the Earth is 6,380,000 meters. But to figure out two REs, because remember, it's two of those, so we have to take that and double it. So when we do that, let's see, what do we get here? 12,760,000 meter sticks. Remember, we have to have this in meters. Okay, so square that, and we get 4,899.54 newtons. And let's see here, we could likely, we'll just round it off to 1 sig fig, because we have 1 sig fig up over here. So 5,000 newtons. All right, so that's the first section. So be sure to watch the Cavendish video I have after this, and also the video indicating how the radius of the Earth was determined, and then from there, how the mass of the Earth could be determined.